I hope you can see my slides.
Yes.
Oh, great, thank you. So good afternoon, everybody. My name is Aleksandra Kaszubowska-Anandarajah, and as Dan said, I'm the coordinator of ICON project, and I will talk a little bit about this project today. But before that, I wanted to briefly talk about why the paradigm of integrated optical communication and sensing is so important. And obviously, that's something that we work on within the ICON project. So I think there are two main reasons for that. The first thing is that we as a society became very reliant on telecommunication networks, as a result, optical networking as well. And that's a result of the progressing digital transformation, which sees more and more of our data, of services we rely on, our economy moving towards the cloud, and obviously being dependent on the access to the cloud and to the network itself. And I have listed just a couple of the most important applications that rely on optical networking here. So the bottom line is that due to our reliance on networks, the network itself became what we call a critical infrastructure, similar to water distribution systems or power grid. And as such, it needs to be protected and made more resistant and more resistant. So if you think about the protection of the infrastructure of the network, well, there's a lot to protect because we have over 5 billion kilometers of optical cable wrapped around the globe. That's enough to go from Earth to Mars 57 times. But that's not all bad, because while these fiber cables transmit data, they also can be used as a distributed sensor, and as such can contribute to actual protection of the network infrastructure itself. So through the combination of these two aspects, the need for protection and the ability to sense using fiber, the idea of joint communication and sensing was born. So very briefly, how can we use fiber to sense? So the propagation of light within the fiber is affected by the external factors such as temperature changes, vibration, strain. And by observing characteristics of the light, such as its frequency, intensity, phase, or state of polarization, we can detect, observe, and often quantify those external factors. And then depending on the type of technology we use for sensing, we also can pinpoint the exact location sometimes along the fiber where those external factors or external events happen. And that's why the optical sensing brings in a lot of opportunities. So the first thing is that we can serve multiple versatile applications, such as geophysics, infrastructure monitoring, traffic monitoring, if you think about cable that might run along the road, and general assessment of the network health itself. Another important factor is that the optical sensing is mostly compatible with the currently used dense wavelength division multiplex networks. However, there are also a lot of challenges that we need to address. So the first thing is that we have, on one hand, high cost sensing technologies like distributed acoustic sensing that provide us with a lot of information, and more specifically, they provide us with the information of location of an event. On the other hand, we have techniques like state of polarization, for example, that in principle could be added at no extra cost. But they, on the other hand, provide us with limited information, specifically no information about the location. Another challenge that we have to face is the amount of data that sensing produces. And if you think about applying sensing across the entire network, you can imagine how much data would have to be stored, processed, and transmitted. Every aspect of this obviously brings in cost, both economic and environmental cost. And finally, even though we talk about integration, really there isn't much progress in the actual integration of the sensing into the telecommunication network. So now moving on to our ICON project. So as Dan said, it stands for Intent and context-aware optical networks. So the overarching aim of the project is to make the sensing an actual integral part of the optical network. And we want to do it firstly by developing what we call a software-defined networking controller for the sensing system itself. And this controller will then interact and interface with sensing applications, being it external application or internal, meaning originated from the network itself. And it will acquire specific requirements of this application, or what we call an intent. Now, the second step would be that the sensing signal, based on those requirements, will be configured and then routed using the SDN network controller across the network in a similar way that the data channels are routed through the network. Using then the data acquired from our sensing systems, we will build what we call the context, which is basically a comprehensive picture of the network infrastructure itself, but also its surrounding. And that is the part that allows us to protect our infrastructure, because it will allow us to, for example, detect the potential threats to our cable, being it, for example, a trawler that drags an anchor along the subsea cable. This context will be built both from the local and network-wide sensing information, but also we want to exploit other sources like the weather reports and marine traffic systems. And finally, the last step is to use that sensing information to transfer that information to our network management system so that the operation of the network can be optimized and using the information that we obtain. So that is, in essence, the concept of ICON. And to move on and talk about exactly what kind of work we want to do is we take a multi-layer approach. So we start at the bottom, so the physical layer, we look at developing a suite of flexible physical sensing techniques, which can be then deployed in different parts of the network. And we are going to develop digital signal processing algorithms to process those huge amount of data, both locally and across the whole network. And as I said, finally, we are going to develop this intelligent controller that can interface with the external applications and also the network management system. And finally, just to talk a little bit about how ICON can contribute to the sustainable future, the first thing is that we aim to protect our network infrastructure, which obviously impacts our economy, society, security. But we also aim to use the information obtained in order to reduce the cost of the repairs to the network. And when I mean cost, I mean both the economic and also environmental costs. And it's particularly important when we talk about repairs of the submarine cables. When we know the health of the network, we can make sure that we operate the network in the most efficient manner, which obviously contributes to sustainability. And finally, even though most of the time we talk about fiber being used for telecommunication, it is also used along the other critical infrastructures, like the gas pipelines or cables connecting offshore wind farms. And so by using the technology developed in ICON, we also can protect these infrastructures, again, contributing to a more sustainable future. And that's all from me. If you're more interested in knowing more about our project, this is the website. And I'm going to pass the baton to Steinar now. Thank you.
Thank you very much, Ola. So I will share my slides here. Turn it into slide mode. Okay, so my name is Steinar Bjørnstad from Tampnet, and Tampnet, we are an offshore telecommunication company. We have subsea fiber cables in North Sea and in Gulf of Mexico. We also do mobile communication in these areas, and this is supported by these fiber cables And also we use these fiber cables for connecting data centers in a carrier network. And it's really critical that this communication is working critical for the energy production. And that's why we are very engaged in fiber sensing. So protecting this subsea infrastructure is very important, because the subsea fiber cables, they are carrying more than 90% of transcontinental internet traffic. So it's really important that we don't have a lot of interruptions on this. And the fact is that subsea activity like anchoring, trawling, and dredging, it's like 40% of all these faults, like 200 cable breaks a year globally. And doing repair of these cables is quite energy demanding and resource demanding. So there are like two different angles on this. When it comes to resources and sustainability, one thing is the repair being demanding, and the other is actually the consequences of an interruption, where you may interrupt energy production or all type of internet traffic, really. So recently, also subsea attacks on subsea power cables or fiber cables, communication cables, have become an important point. So we see also with these cables and with fiber sensing a lot of application related to geophysical things. So like subsea landslides, for example, that's also important. That may actually destroy a cable. So that's also something we would like to protect against. It's like what they do currently is to inspect cables and subsea infrastructure by going out with the ROV, for example, every second year, doing inspections. But it would be much more efficient if you could pinpoint whenever actually something has happened, where to go and inspect. And this is something that we hope to achieve with the fiber sensing. And also in CCS capture, carbon capture, for example, it's very important to monitor the oil and gas wells, old wells where you are pumping down the CO2, because the pressure is changing when you do this, and you need to ensure that it's stability in the areas around this. So we see also these as applications for fiber sensing. So this is an example of an earthquake observation, and we see the waterfall here, which is from distributed acoustic sensing. Along the x-axis, you can see the length of the cable, and on the y-axis, you see the time scale. And typically for earthquakes is that they typically are seen over the whole cable. Depending on the direction and distance to the earthquake, you see it weaker or stronger, and you see it at different times on the different parts of the cable. But a good point with this is that we do have seismic observation stations onshore, different places. But if you really want to have a good knowledge about earthquakes and what is going on, you would like to observe as close as possible. And there are also smaller earthquakes that you can't see onshore that happens offshore. And with a cable, you can actually see this, and you may even be able to do tsunami warning. So this is really important things in research, I think. However, doing monitoring of all these cables, you will have a lot of data and a lot of data sources, and you will need to do some kind of correlation. And also, I mentioned several applications of this monitoring data, and we may use the same raw data for several applications. There will be several interest groups, and we need somehow to group it, somehow to shape it and filter it into these different groups. Thus data may also be sensitive in the way that we may be able to track, for example, military vessels, and that's maybe not that good. So somehow we need to filter out this and make sure also from a security point of view that we don't do anything wrong. So this is really, I would say, key research topics and challenges that we need to address. So here are a couple of examples where we have used fiber sensing. And this picture down here is from a cable repair. It's one of our cable that has been partly damaged by trawling. And this is how it may look, but now we are using fiber sensing on this cable. So whenever there is a troll approaching, we can see the troll approaching, and we can also see if it hits hard or heavy, if that happens. But most of all, we try to tell people who are approaching with anchor or troll that they should stop and turn their vessel and be careful when approaching the cable. To the right here, you see there was a fisherman calling us and say that, well, had an accident with my troll, it's stuck somewhere. Well, we looked at our sensing equipment and we couldn't see any response. And he tried to drag his troll and there were no response. So we said, okay, you are above or very close to our cable, but it can't be our cable actually. So we don't need to do any inspection or anything. And then he had some help with picking up his troll, and this is it was stuck in some kind of frame from a car or something. So that's what we see in this picture. So that's also a useful application of the fiber sensing to make sure that if something is stuck somewhere, troll or something, and actually identify if this is a cable or not. So proactive alarming and scaling fiber sensing and being able to separate the information to different users, that is key concerns and really something that we see as very useful research topics. Thanks. I give the word now to Petr.
Thank you, Steinar. Okay, hopefully you can see my screen. My name is Petr Munster. I'm from the Brno University of Technology. And you could hear from my colleagues that we can have different techniques we use for monitoring using optical fiber. So from the definition of sensor, it's a device which converts any physical measure into alternative form of energy. And in our case, it's an optical signal. And if we use optical fiber as a sensor, there are so many advantages. So it's right now a really hot topic to use this optical fiber, not only for data transmission, but also for sensing and increase the resilience of the fiber infrastructure itself. If we look on the classification of how we can classify optical fiber sensors, that it's not only from the point of view of operating principle, so because there are different ways how we can really evaluate or we can measure the physical entity from the fiber, but we can also have a look on the point of view of application or measurement, if it's for temperature measurement or pressure strain. And of course, based on the principle, we can have a look more deeply on the technology, and we can see that the number of technologies is growing up. So there are so different technologies you can use, for example, for a distributed dynamic and strain measurement. In our consortium, we are mainly using this backscatter-based sensor. Mostly it's a distributed acoustic sensor, but we also have access to distributed Brilliant scattering. And the principle is always the same. So we have a really good laser. We modulate this optical signal, amplify it, and then we have fiber on the test. From the fiber, we receive the backscattering, and based on the principle, it can be the Rayleigh scattering or the Brilliant scattering. And of course, based on the principle, we also have to think about the modulation, because we can have correlation aided OTDR, time expanded OTDR, or we can have also coherent distributed acoustic sensing. So there are different approaches, but there are the same advantages and disadvantages of the technique in principle. In term of advantages, it's mostly it's single-ended measurement. So we only need to have access from one side of the fiber. We can localize events over long distances. Usually these systems can work over tens or hundreds of kilometers with really good resolution, about units of meters. And we can use already deployed optical fibers, which is a really huge advantage. In terms of, let's say, disadvantages, the price of this device is really high. So it's not relevant that we have one system for one fiber. So we have to think also about the real application of the fiber optical sensing device. And also the amount of data generated by this type of sensing system is really huge. So we can generate about terabytes of data per day. And of course, if we generate pulses and then amplify it, we usually go to nonlinear effects, and this phenomena can interference with data. So the interference with data is one of the challenge if we would like to have one fiber for data and for sensing. You can see two examples. If we apply some strain on the fiber, and this is a waterfall graph, and we can see number of measurements and the position. So for each position, we can receive the information along the fiber. We are not focusing only on infrastructures which are outside the building, but we are focusing also on infrastructures inside the building. In terms of polarization-based sensor, we analyze really the state of polarization in optical fiber, so polarization of the light itself. There are two main approaches. You can use a polarimeter, which is a really nice device. It's not so it's quite expensive, but you really have Stokes vectors, so you have information about current state of polarization. In case of polarimeter, simple polarimeter, or mostly it's a simple polarization analyzer, we are using polarization beam splitter, and we use a balanced photodetector. This system is really low cost. It works. It's not so sensitive in general. The polarization is not so sensitive as, for example, distributed acoustic sensing, but still we are really achieving really good results in terms of measurement values along the fiber infrastructure. We can measure over, again, tens of hundreds of kilometers, but of course the localization is not very simple. Sometimes it's impossible to localize events. Another advantage is that we have really low sampling rate compared to distributed acoustic sensing. For example, we can have only tens of kilosamples per second, which is really low. But we mostly have to access to both ends of the fiber. So we need to send the signal to the fiber, and then we measure the opposite side of the fiber. But the advantage is that we also have experience that we can use directly data signal, so modulated data, and evaluate this data signal and polarization of the signal. Again, here we can see a few examples. This is for the cable manipulation, so we can nicely recognize that there is a nice reconnection of the fiber on pitch panel, and there's also different signature when you compare it to the fiber cut. But polarization is not sensitive only to this really strain or vibrations or manipulation with the cable, but the polarization is also sensitive to temperature. So we can also see the polarization fluctuations or state of polarization changes just because of temperature change along the fiber. And what's now very promising solution is that we can use also data transceivers for not only monitoring, but also for sensing. The current transceiver usually give us information about the received power or transmit power, but also about OSNR, differential group delay, and so on. From these parameters, we can mostly see that the fiber is bended or there is something going on near the fiber. We also have experience that if we combine these monitoring parameters with artificial intelligence algorithms, then we can correlate these parameters. We can really recognize the information about the events along the fiber. If there is some kind of heating or bending of the fiber, we can be sure what kind of event is going. It's going to be happen, and with today coherent transceiver, because there is already this coherent transceivers are already using state of polarization analysis. So right now, these coherent transceivers also can give you information about state of polarization. So you can also receive the information about state of polarization changes. So it's not only about power level and so on, but also about state of polarization. But right now, this is still under research, and most providers of the system are just give you information about parallel OSNR, and this is still under research. So this is all from my side, and now let me give a word to Florian from Atran.
Thank you, Peter. I hope you can hear me. And yes, okay. So sustainable future networks. Hi, I'm Florian Azendorf from Atran, and I will talk a little bit about applications for fiber sensing. So there are multiple main applications in telecom networks, intrusion and security, power utilities, geotechniques, water oil pipeline detection, and smart cities traffic monitoring. And we did some work on the power utility stuff, but within ICANN, we want to focus on telecom networks and intrusion and security applications. And the first thing we have to do is how can we integrate fiber sensing into the telecommunication network. And I will focus during this talk about on that, what needs to be done and what have we done so far. And the first thing it did is, okay, let's use a standard coherent transceiver on one side and another one on the other side, so that we have two network nodes, and we simulated this new two network nodes somehow with these transceivers, and we had a fiber span, including a booster amplifier and a pre-amplifier, and we had our distributed fiber optic sensing system, which is here an coherent correlation OTDR, and this one was coupled or multiplexed together with the data channels. And then we had the fiber span, as I said, the pre-amplifier, and then we had the receiver. So here in this setup, we used the so-called co-directional probing. So the data channels and the sensing channel will propagate in the same direction. We used here 33 gigabaud transmission channels, so 100 gigabit per second with QPSK and dual polarization. And what we saw, or what we thought, is that the main contributing nonlinear effect is either cross-phase modulation or cross-phase polarization modulation and stimulated Raman. When we put the sensing channel a little bit out of band. So here in this case, we used an in-band technology. And the first thing we realized is that when we use the QPSK modulation format, that our prefab error bitrate experienced some penalty. And it was here in this case a 3 dB penalty. So that it was not possible when we go down to 10 to the power minus 2 bit error rate. It was not possible to detect the data channels. So, and this is the first important point here. So this is the so-called required OSNR to achieve joint communication and sensing. So this parameter was now taken for standardization. So this is something that I will talk later about, so the standardization process. But this is now one parameter that is or will be defined in the next ITOT standardization. And the next thing is that we did some kind of probing signal smoothing to get rid of these penalty effects. So if you smooth your signal and you have not sharp transition like you would get it when you have a rectangular shaped signal, then you can reduce this required OSNR up to 0.1 dB. And this would mean that we can do co-directional probing with data channels. The other approach would be to use counter-directional probing. So the same setup, but now we send the sensing signal or the sensing channel in the different direction to the transmission, to the data channels. And if we do that, we can also go to higher modulation formats, which would mean higher modulation formats are more efficient, which means they are more sustainable if we reduce or if we can transport more data. So this is one point. And the nice thing is that with the counter-directional probing, there was no OSNR penalty. So the distributed fiber optic sensing signal and the data channel could coexist together in a lab trial. So of course, in a lab trial, we used a fiber spool. There were only 2 connectors, so no extra losses. So that needs to be tested if somebody wants to volunteer in a real life network, whether it works or not. And that brings me to the standardization part. So we are actively working in the ITOG standardization group 15 Q6. Q6 is question number 6, and here we're working on distributed fiber optic sensing system for terrestrial optical transmission systems. And in this standard, or in this paper we have submitted, we defined the in-band and out-of-band sensing, and also this required OSNR parameter, and what are possible strategies for fiber optic sensing. Also, this sensitivity and crosstalk and such things are defined in this standard, or will be defined in this standard. So that brings me almost to the last slide. So we want to talk about sustainable networks, and if we have optical data transmission, then the goal for us is resource and energy efficient data transmission. So how does fiber sensing contribute to that goal at the end? So, and first of all, there is the direct impact, right? And there's no direct contribution from fiber sensing. And the next disadvantage is it consumes spectral resources. And another disadvantage is, from a sustainable perspective, it consumes power, right? So we need more power to have joint communication and sensing. But there are also indirect benefits. And they are protect fiber infrastructure. So that means if we can detect events or different events, it is possible to let the network operator know that something happens, and maybe that is a potential threat for the critical infrastructure. Another thing is if we combine sensing and monitoring in fiber optical networks, then we are able to detect losses. So, and then we can also say, okay, there's a loss. Maybe we need somebody that splices, which adds additional loss. But then if the fiber has better quality parameters, we can also increase to higher modulation formats, as I have shown 2 slides before. And then this next advantage is that we can avoid service interruption, which means our service runs flawless. And then we can reuse existing fiber. So that means the fiber is deployed, as it was said before in the other talks. And that means there's no extra cost, so investment cost of the network operator. So they can just reuse the fiber. And that means also no extra cost in digging into the ground to deploy the fiber and so on. And then it's efficient to use it in installed assets. So we can do it in the same network as I have shown it before. But there's still a but, and this is the key enablers. So to enable joint communication and sensing and to have sustainable networks, we need more ports for scalable and efficient measurements. And to do that, we need to optimize our processing technologies and of course the storage technologies. And the last, and I guess the most important one, is smart event filtering. So that means at the end that the network operator wants to know, is it a low-risk event? Is it a high-risk event? And we need to provide this information to the network operator. So thank you for your attention, and I hand over to Dan.
Okay, thanks, Florian. Thanks all the speakers. So again, folks in the audience, we encourage you to put questions in the chat and join the conversation here. I'm going to jump in with a few questions of my own to get us started. So actually, what I wanted to dig into first is really what's the state of the current technology, right? So Steinar was showing there that there's something going on where we're detecting these trawlers operating around the ships, and Florian, you were showing that it looks like there's standards work going on and things, and we saw all the different techniques that are out there. So why do we need a EU project to tackle this? What's kind of the new bits, and how is it really being used in practice today in terms of sensing? Maybe Florian, since you were just talking, I'll feedback to you there. If you could just elaborate on what you were talking about there and your assessment of the state of the technology today.
I would say we have several interrogators, and we have several interrogators that cost a lot, so high costs. And I guess the idea is to combine different sensing techniques to reduce the costs. And I guess that is one key enabler. And the other one is that we as engineers love to look at time domain or frequency domain series and analyze them and maybe do further fancy signal processing. But a network operator asks clearly for an application because they have to pay for these interrogators, and then they want to have an application or a benefit out of that. And I guess that is the current state, that there are a lot of sensing techniques, but the question is, how can network operator use them to get benefits or to get an economic application where they can gain some money from. So.
And just to be clear, so when you talk about interrogator, so that's a distributed acoustic sensing, usually a reflectometry-based sensor, yeah. Okay, and Steinar, you want to jump in?
Yeah, if I could just add to this as a telecom operator. It's let me tell this as a story. So last weekend I discovered by fiber sensing that there was a troll crossing our cable, going back and forth. and giving signals that he was going back and forth. And I contacted our network operations central, and after I also checked the AIS and found which vessel this was, and they contacted someone who contacted the vessel, and they stopped going back and forth. But I think this also tells where we are today. It shouldn't be me as a researcher doing this job. It should be the first line in network operations. So as Florian say, we need an application. We need some more intelligent processing, correlation of signals and different data sources that actually gives abstract of the information to the first line supporting network operations that can do the action.
Very good. And Petr, you had a comment also?
Yeah, I would definitely agree with my colleagues, because it's not only about the sensing technique, because that's we already have here for tens of years, but right now it's about joint communication and sensing in a single fiber, and also about not only sensing but monitoring and intelligent control system. So it's this is the ICON project about.
Very good. And I guess to add to Steinar's example there, so there was a North American operator who was reporting recently that they were doing monitoring in their network, and so the terrestrial network, so the terrestrial side of it, right? And they correlated their monitoring signals, I guess, with construction sites to identify where there's construction activity and to avoid potential fiber breaks there. So we're seeing this in the terrestrial and the submarine environment. And but to Florian's point a little bit, I guess, I know some network operators are saying that, well, we can't afford to put these DOS units all over our network, right? So there's still work to be done on the techniques themselves to make them more affordable and somehow make them part of that optical communication system. Is that right?
Yes, I guess it is right that data and sensing channels can coexist in the same fiber. And I guess one big thing is to increase the number of ports. So what kind of switches can you use? Can you use typical MEMS-based switches that are used in multi-port OTDRs? They are based on mechanical components. They can cause vibrations. What happens if you see them in your DAS system? What happens if you see them in your SOP system? So is then an interesting component gone for the frequency domain? And that, I guess, are problems we have to think or we will face in the upcoming years. So how can we increase the scalability? Are there other techniques? Can we use switches that can switch fast? And what means fast? Do we have to measure continuously over hours, or is it enough to measure every 2 to 3 hours for 10 minutes to see is there a change in the signal? I guess it depends on the application at the end.
Yeah. Ola, do you want to jump in on that? Yeah.
Yes, so I guess I wanted to say that while we are talking mainly here about DAS, the important point is that with the ICON, we want to look at other types of sensing which are less expensive and that can be employed in the parts of the network, like an access network, where obviously it's not sustainable to use very expensive sensing techniques. And the other aspect is the flexibility, and when I was talking about routing the signal, so it is not necessary probably to have all these big or expensive signals going through each part of the network all the time. But if we detect or we know that there's something going to be happening around certain part of the network, we can then deploy that signal over a specific part of the network for a time being to monitor and make sure that nothing is going to happen. So this is also a part of ICON, right? To find other ways to monitor the infrastructure rather than just using DAS.
Very good, very good. So question here from Hajar Benuri. So this is for Petr. So your team at Brno University of Technology is contributing to the ICON testbed activities. So maybe describe how these test beds support the validation of sustainable network concepts.
Yeah, we are leading the work package, really focusing on test beds. Those test beds let us combine optical data signal with sensing, and in really realistic condition for different topologies, which is a great advantage. And with those test beds, we can cover the gap between the simulation itself and between the real application in a real deployment, because there's no possibility that we can always use for a different type of infrastructure, real network. So that's why the test beds are very important.
Very good. Maybe, Ola, can you elaborate? What are the different types of test beds that are being explored in the ICON project?
Well, there's lots of them. So first of all, we have the network itself, that's StampNet. So we have a proper network at which we can gather data. We have our Open Ireland testbed here in Ireland. We have 5 deployed in Atran. We have a testbed in Brno. There's too many to mention them all. I don't know. Am I missing anything, Petr?
No, definitely you are right, and it covers really short reach test beds, long reach, so we can simulate all this and combine these different technologies for different setups.
Then, so we're hearing about well, many different types of test beds, different types of applications. Is there one kind of key area that we see as the most important application for this new technology? Is it going to be in the submarine systems, access networks, or are fiber to the home going to be using sensing in the future?
Possibly, but I think we can clearly see that from the consortium point of view, and I think also from the sustainability or impact, the submarine cables are something that are really important to protect, because just the repair of the submarine cables is so extremely expensive and also have such a high impact on the environment, because as Steinar has been educating us, to repair a submarine cable, you need to use a special ship that's extremely expensive, costs between $50,000 and $100,000 a day, and can generate or produce up to 400 tons of CO2 a day. So if we can avoid the damage, that's a huge saving. If we cannot avoid the damage, but we can pinpoint the exact location of the damage and shorten the time to repair, that's obviously huge savings, both in terms of economy and environmental impact.
Very nice. And it's getting to the topic of environmental impact. So we're hearing about more efficient operations and so forth, but there's also the geophysical sensing aspect. And I know that a lot of geophysics scientists, the oceanic researchers, are really excited about the opportunities around using the cables in the oceans to be able to do sensing. Where do each of you think the best opportunity is from an environmental standpoint? Is it the environmental monitoring or the kind of more efficient networks and operations that we get from that? Maybe Steinar, do you want to jump in first?
I can jump in. So, yeah, I think from a network operator perspective, first of all, it's what is the most important for us is that the communication works. So it's protection of the infrastructure and having an efficient way of finding faults and all that stuff. But it's more like actually an added value, potential added business, using it also for other applications like geophysical applications, earthquake monitoring and tsunami warning. I mean, it's really that's really a good thing for everyone. It's really a global thing, but challenge is of course the There you also have some challenges in the sensing technique with distance. You should be able to monitor, for example, across the Atlantic, the complete cable, and preferably with a high resolution. So recent research is progressing on this, but this is also, I would say, on the edge of what is possible. So, so from a network operator perspective, we see this as also an added business, actually. That the whole fiber network, it's very interesting and fascinating, actually, that the fiber network is, all investments is done with respect to communications, but we see that it's a sensor network that can add value on top of that.
Very nice. Petr, you have a comment?
Yeah, I just want to mention that for us, we are mainly collaborating with security agencies. And it seems that fiber sensing is also in their interest. So for us, it's mainly right now security. But we can see so many different applications, and I believe that in the near future there will be more and more application. Right now we can see that there are companies in the US that are really doing smart city monitoring using distributed acoustic sensing and so on. And this is also one goal of the ICON project, is also to create data sets and sharing these data sets with the community, which can provide also really the information that we have all these data sets, and researchers along all over the world can, let's say, look for new applications.
Great, great. We have another question from our audience here. So Colm Browning is asking, how much more difficult is urban sensing and event correlation compared to oceanic? You have all that long fiber going across the ocean to correlate these earthquakes. I guess, how hard is it to track buses and cars through a city? And he's also asking, will AI play a role here?
I guess every network or different networks come with different problems you have to solve in the software. So for instance, in a terrestrial network with area fiber and buried fiber, you get some noises due to wind speed, and that means that you have really low frequency components, and you have to filter them out. So you have to adapt the software, and then you have to find first the events, and then you have to train something, either natural intelligence or artificial intelligence, to detect these events. Right? That's the main difficulty from my perspective.
Yeah, I think just
go ahead, Steinar. You don't
very short comments. In subsea fiber cables, it's mostly silent. In terrestrial cables, there are always something going on. So it's much more challenging, I think.
Well, I guess that's where this context awareness comes in. And with the ICON project, you want to bring in other data from, you talked about these AIS systems for the shipping, and I guess there could be information about construction sites, one example, other things. Is that some of the motivation behind the context awareness? Ola, do you want to comment on that?
Yes, definitely. So several things. One is, yes, possibly filtering out the noise or figuring out what is a true threat to infrastructure and what is not. The information of, as Steinar mentioned, the position of the ship is something that definitely can be useful. The question is how we're going to integrate that into the network, or how we're going to interface. I think it's a very challenging aspect. Yes, and finally, as I said, the information about the construction is something definitely that we can use, because, as I said, if we know that there is some kind of work going on or plan to be going on around some of our infrastructure, we can ensure that we have extra sensing technology deployed over that piece of fiber, so that we can monitor it in real time and react to it in a timely manner.
Okay, very good. Well, we'll close the webinar with that. We've come to the end of our time. I want to thank our speakers so much. So we have Ola Kaszubowska-Anandarajah, Steinar Bjørnstad, Petr Munster, and Florian Azendorf. Thank you for sharing your valuable insights today. Also, a special thanks to the audience for joining us and contributing to today's discussion. If you'd like to learn more about the ICON project, so there's a link to it in the chat here, and you can follow them on LinkedIn. And then this webinar is part of our Sustainable Future Network series hosted by the Connect Center. We hope you'll join us for future sessions, and as we continue to explore the research shaping our digital future, make sure to sign up for our newsletter. There's also a link to that in the chat, so you don't miss our next webinar.